So this week I'm going to talk a little bit about exchange interactions, and then second lecture will be about spin waves using quantum operators, just to show you how easy it is to do that. Right, so some of this is, well, I think a lot of this is actually advanced undergraduate stuff, but I'm never quite sure what's been covered in the various courses people have done. So I'll just go back to basics just to make sure we don't miss anything. The exchange interaction, what do we mean by the exchange interaction? Well, we just mean that there's a difference in energy between states where the spins are parallel or anti-parallel in a system. So, for example, in a ferromagnet, as I've drawn at the bottom here, you have, if the spins like to be parallel, you're going to favor the ferromagnetic state here. And if they like to be anti-parallel, if there's an interaction that means that neighboring sites are anti-parallel, you'll favor an anti-ferromagnetic site. Okay, so that's very simple. So let's just look about how that can be parameterized in the simplest possible case. So that would be the Heisenberg interaction. So we're going to talk about spin a half spins in this lecture, just to keep things under control. So let's just think about two spin a half particles and the spin operators. So if we have two spin operators, one for the particles on two different sites, A and B. So this would be the spin operator for telling you the spin along the z direction. Okay. So the total spin of the system of our two particles on two neighboring sites would be the this total spin here. So that's the sum of the two spin operators. So there's two spin operators that we use in magnetism. Of course, one is just for the spin on a site, and the other use for one is the spin squared on the site. So the second one, if we square this first equation, then we're going to get the second equation here, where we've now got a dot product between the two spin operators on a site, telling you the moment along the z direction. This is here, but now we've got the operators here for the moment squared on one site and the moment squared on another site, and the total moments squared. Okay, so these two spin operators, the eigenvalues you get here for this first one will just be the spin, if you like, and the eigenvalue for the second one will be s plus 1. Okay. Right, so this eigenvector then is going to be fixed by the particle you've got on the site. So in the case of the spin a half, it's just going to be a half times a half plus 1. So these two things here are going to be constant, this one and this one. Those will both be a half, 3 fourths if we're using spin a half. So the eigenvalues, possible eigenvalues for the total spin, then would be 1. The eigenvalues of this total spin are, let me just rub this out so I can see what I've written here. I'm not sure what this bit means here actually, so let's just forget that. But this is the more important bit here. The spin squared operator can have eigenvalues of the spin squared operator then can have eigenvalues of 0 and 2. So let me just reconstruct that. So if the spins are up, up, or down, down, then one would get the 2's. And of course, if you have an up, down, then you would get the 0. And as I said before, the eigenvalues of the individual operators on the sites then would be a half times 3 over a half, and that would give you the 3/4. Okay, so the so the two things that are changing in this equation then are this dot product and this thing here. Okay, so these are the possible states you can have for the eigenstates actually for this operator where we dot the two spins together. Okay, so we have these different possibilities. So if we have up, up, or down, down, we have the quarter and a quarter here. And if we have the combination up, 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 down, plus down, up, we also get a quarter. And then if we have the antisymmetric state up, down, minus down, up, we get minus 3/4 here. So this operator then is going to have two sets of eigenvalues, these ones here, quarter, and then minus 3/4, which is summarized at the bottom here. And the key thing that determines which of the states you have is the total spin here. So that would be the total spin of 1 would give you the quarters, and the total spin of 0 would give you a 0. So this would be then the state where the spins were in antiphonetically aligned, and here we'd have the state where they were lined next to each other. So what we've done then is to find a way of expressing the difference in energy between these two states in terms of this operator here, which is the Heisenberg interaction. So this is just a very simple way of parameterizing the difference in energy between having a state where spins are aligned and anti-aligned. Okay, so one can sort of capture everything together and write a Hamiltonian here. So what we've got is imagining that we have these two states, a singlet state and a triplet state. So one with the spins aligned and one anti-aligned. And here you can see how you would write the Hamiltonian in terms of this operator to get the right energy. So here the bit that changes is going to be the obviously the difference between in energy between the two states, and here's your operator. Okay, this energy here, if we're dealing with just localized spins, we call this the exchange energy J. So then you end up with a magnetic Hamiltonian then. which looks like this. So this is the Heisenberg Hamiltonian, and you just forget about this this shift, or you include that in some other part of your Hamiltonian. Okay, so we're going to use this sort of expression that describes the difference in energy between the two states in spin waves and other things later. But let me just say some things, some general things about where this difference comes from. So the material with the sort of highest exchange interaction, I guess, is something like hydrogen, where you literally have two spins very close to each other in a hydrogen molecule, and there's overlap between the atomic states, and you find that in hydrogen, of course, that you have the lowest energy state is where the spins in the two atoms are anti-aligned. So where does that come from? Well, fundamentally, of course, the exchange interaction in solids that we work on is not a direct interaction between the spins. It's an indirect interaction coming from the electromagnetic force. Okay, but it's mostly coming from the Coulomb part of that force, through the fact that choosing a state with a certain spin wave function puts constraints on the spatial wave function. So it's that gives you the exchange energies in solids, in the things we're interested in. So you can see how that comes about, as I said, by looking at the hydrogen atom, and I've illustrated that here. So we've got our two nuclei here, and this is the spatial wave function of the electrons. Okay, so if you you know obviously from basic quantum mechanics that that for fermions the overall wave function has to be antisymmetric. So if you have an antisymmetric spin part, then the spatial part will be symmetric, and vice versa. So this is this picture on the left here. We've got an antisymmetric alignment of the spins. So the spatial wave function has to be symmetric. And what you find out when you work out what spatial wave functions actually look like and plot out the charge density is that if the spatial wave function is symmetric, it'll tend to look something like this one here. So how might we do that? Well, of course, to make if we start with our molecular orbitals, so we call this atom here A and this atom say B, and we imagine that we have electron which we label electron 1 in orbital A, and then we want to construct some symmetric orbital. We would just start with something like this, and now to make it symmetric, we would have to add the term with the two electrons swapped around, say like this. Okay, so that would be a symmetric orbital. So when one works out the charge density corresponding to that, you find it looks something like this. Whereas if you make this antisymmetric, you find that there tends to be a region of cancellation here in the middle. Okay, so what's the effect of this? Of course, this means that this region between if you put the electrons in this region between the atoms, you get an interaction, a Coulomb interaction that lowers the energy of the system for this state over this one. So there's two contributions actually to exchange energies. This would be the Coulomb interaction. So this would be the direct interaction here. But of course, in the Schrödinger equation, there's also a term which is tells you the derivative of the wave function. So of course you've got minus d5 by dx squared at the front there. So the curvature of the wave function is also important, and that is actually a kinetic energy term. So when you work out the total difference in energy between these two states, you have to include both. So the exchange interaction can be in principle driven by differences in kinetic energy as well as Coulomb interactions. Okay, so that's where the exchange interaction comes from. So here's a couple of examples then. So often we distinguish between direct exchange and kinetic exchange. So this is to do with which of those two terms I just mentioned actually drives the difference in the energy. So direct exchange is when it's is driven by the potential, so the Coulomb interaction, and the other case you can have is where the kinetic energy term is important. And I'll explain the case of super exchange, where it's actually the kinetic energy that drives the reduction of the energy of one of the states favoring magnetism. So in the metals, for example, it's this one that's important, and this can be the case where you have a mediating atom between the two magnetic atoms, such as in the cuprates. This term would be important. So here's the derivative term that I mentioned. It's in the Schrödinger equation, obviously. Okay, so I've already mentioned this, that the hydrogen molecule actually is a very good example of exchange interactions, and early last century this was all worked out, the different wave functions here, and you can work out the difference in energies. And this is an interesting plot here that you may already know. If you work out the energies of the two states, so you bring together your hydrogen atom with two spins like this, or two spins like this, you find actually the singlet state. So this state forms an atom, but actually the triplet state at this level of approximation, it's called the London-Hillier approximation, I think, doesn't even form a bonding state. The exchange interaction, the difference in the energies is so big in the case of the hydrogen atom. Okay. So in metals, as I said, it's the Coulomb interaction that's the dominant thing, and one way of visualizing this is through the so-called exchange hole, which is illustrated here. So you can imagine that if a metal electron is whizzing around in a metal, when you work this, the ideas I've been explaining to you out for a system of many electrons, you find that that around a given electron there's a difference in a probability of finding an electron with the same spin and the opposite spin. and this is called the exchange hole. So that difference gives you a difference in energies, and can favor, in general, it tends to favor ferromagnetism in metals, but as we'll see later, there are additional effects due to the Fermi surface which can lead to it favoring incommensurate structures, and sometimes anti-ferromagnetism. Actually, some metals such as manganese have anti-ferromagnetic structures. Okay, so let's have a look at a bit of a super exchange, very topical because of superconductors such as cuprates, which are showing super exchange. So what is super exchange? Well, super exchange is where you have a magnetic site. This is lanthanum cuprate here, for example. So the copper would be copper 2+ in this compound here. So that would mean that there'd be one spin in the d orbitals. You'd take away the 2s electrons, the 3s, and be left with one hole in the d's. The last d state's not filled, so you'd have spin 1/2. And then you'd have in the structure, of course, you have copper, then oxygen, and then another copper here. The oxygen orbital, if you look at the periodic table, you find actually oxygen is a very big atom for its atomic number. So that's because oxygen is 2-, and putting on the two extra electrons makes the p orbital very big. So this figure actually is drawn using the ionic radii of the different atoms. So obviously they doesn't take account of the shape of the orbital, but it just gives you an indication of how big the oxygen is. So there's a lot of overlap of the orbitals through the oxygen. So you have, and this is important in the exchange. Oxygen isn't the only atom that can do this, of course. Another one is its friend fluorine. So obviously you can have fluorine minus, which is also a big atom, and you can have insulators such as manganese fluoride here, where you get super exchange through the fluorine atoms. So here we have schematically what it looks like for the cuprates. Then this would be the copper d orbital here, and this would be oxygen p orbitals. Actually, the oxygen is supposed to be in the middle here. This is a p orbital, and there is the overlap. Of course, there would be 2 oxygens in the p orbitals here, and these are the single spins on the copper. So then this, because you have 2 compensated electrons here, the oxygen is not magnetic if it is 2-. Of course, one can remove one of these electrons, and then in principle, the oxygen could also have a moment. And if one measures the spin density in some oxides, one can see that there is one can have some of the moment on the copper. Oh, sorry, on the oxygen. But in the simple picture that we have here, where these are not, there's no doping or anything, then we're not expecting to have any moment on the oxygens. Okay, so how do you understand the exchange energy for in the case of super exchange? Well, the easiest way is to use second order perturbation theory, which is a way of understanding in general why you can lower the energy of states if you let electrons move around more. Okay, so of course you can think of the wave function of an electron. If we imagine that it's sort of highly localized for some reason, it's going to have a high kinetic energy because the derivative term in the Schrödinger equation will be large. But if we can sort of spread it out, it will lower its energy. So spreading out actually means that you're going to allow it to access more states, more quantum states. Okay. So if you think about, if we think about just some set of states in general in perturbation theory, okay, here's some states, and we can have the ground state equals 0, and then our excited states, we can have n excited states up here. And if we turn on an interaction to the system, so the interaction means that this matrix element is finite. Okay, we can see actually just from this second order perturbation theory estimate of the change in energy of the ground state, that the energy of the ground state will always decrease. Why is that? That's because the matrix element squared is obviously going to be positive, and we know that the energy of all the finite states here is bigger than the ground state. So this denominator will be will always be negative because n e is going to be greater than n0. So that will mean that any interaction between the ground state and all its friends up here will lower the energy of the ground state. So that's a common phenomenon in physics and chemistry, and goes with various names, such as level repulsion. So we mean by that we're repelling the lowest energy, energy downwards. And this is a way of seeing that allowing a system to, allowing our, our state, our first state where the electron's sitting, to interact with other states can lower the kinetic energy basically because of this. Okay, so let's have a look at this in the context of exchange interactions. So here we have some exchange interactions. So if we were to have this situation here that if we were in the antiferromagnetic state, we had more possible excited states than in the ferromagnetic state. In the qualitative terms drawn here, we would find that the energy of the antiferromagnetic state would be suppressed more than the ferromagnetic state. So this would favor antiferromagnetic alignment of the spins. So we're imagining in this case the state we're talking about is going to be the copper oxygen copper, okay, or some other super exchange trio of atoms. And then what we're saying is that if we find that this allows us to construct more excited states than this, then that would mean that the antiferromagnetic state would have a lower energy. So in order to sort of see what actually happens, we have to think about the different, we have to write down a Hamiltonian and think about the different energies of the system. So I'm not going to write a Hamiltonian because I don't want to get too bogged down here, but so I've just written down some of the possible energies of the system. So we've got two d orbitals on our copper atoms, an oxygen p orbital in between. The energies of the system would be the energies of the d orbitals and the p orbitals. So for when we occupy them, we have to count the energies of those things. And then we could have some Coulomb repulsion. So if we put 2 electrons in our d orbital, we have to include that as a cost. And then we can have a hopping term where this is a matrix element then, where we can hop between our orbitals. Okay. And then we're going to label a system with 2 sites then. So the d site's going to be 1 and 2, and then we've got the p orbital. So here's our 2 possible candidate ground states. One which we have antiferromagnetism in the sense that the neighboring sites are antiferromagnetic. So we have up on one site, then we have both of the p orbitals occupied, and then down on the next. And ferromagnetic state would be where we have up, and again the same. Okay, so here we've got a list of possible excited states from those states. So we've actually got the ground states here on the top. So if we take this one first, for example, this is a ferromagnetic state. So we've got the up. Oh no, we don't have the up and up. What do we have here? Well, I haven't actually got the original states here. So let me just draw those on. Oh, yes, I have. So this is the original state. So this is up, up, and up down the middle. Okay. So if you have this state, what excited states, and this state has some energy, right? We've added it up. Actually, here's the Hamiltonian on the top here, and I said in words, so we can add up these different terms to work out the energy of the state in principle. So we have this and this. And then the other possibility was the antiferromagnetic one. So in terms of the ground state, then these different terms actually would be the same for this state and this state. So because the interaction term, for example, is determined by how many atoms you have on how many electrons you have on the same atom here, this would be the same. And then this is the hopping term, and the occupation of different orbitals would be the same. So these would be degenerate. These two states would be degenerate in the absence of interaction with other states. Okay, so the way you understand superexchange then is to think about possible excited states from these. So in this case, what can we do? Well, we can move one of the electrons on the oxygen onto the copper. Okay, but the one you move has to be the one with the opposite spin to the site you're going to. So you can actually move that one to there, or you could move this one to here. So there'd be two states like this, and that's really all you can do for the ferromagnetic state. Whereas for the antiferromagnetic state, you can move this one. Let's see, so there should actually be more possible states. So we can move this one to here. And then we would get this state here. So I lost my pen, so this one here. If we move this one to here, we'd get this with the two states here with a cost of U in energy, so it would be a higher energy state. Okay, and then we can actually also move this one to here without changing its spin, and we get this one. And in this case, we could also move this one to here. So then this gives us the same intermediate state here, but then we've got another possibility of moving this one to here. So in the case of the ferromagnetic state, though, once we're in this state, we don't have any more possibilities because we can't move this one to here, because then we'll have two states, two electrons in the same state. and we can't move this one to here. So we're sort of blocked. We can only go back to the original state. So the antiferromagnetic state, because you can carry on moving, there are more states, excited states possible in the antiferromagnetic case than the ferromagnetic case. So when you add up all that properly, when theorists add it all up, they find that this lowers the energy of the antiferromagnetic state with respect to the ferromagnetic state. And that's how the super exchange comes about, because it means there are more virtual or intermediate states allowed. When you work all that out, you can find a simple estimate for the exchange energy. The difference in these two states is something like this. It comes out to be T squared over U. So T squared is a measure of the overlap of the states, and U is the energy of putting 2 electrons on the same copper. So in order to have a high exchange constant in a super exchange, you can see you want to have a large T and a small U. Okay. U doesn't actually change that much. I think if you look through the periodic table, it changes a bit. But T, of course, is due to the overlap of the orbitals. And that's the special thing about oxide metals, is that the T can be quite large. So in the cuprates, for example, one can get this exchange constant, the T being about 0.33 electron volts, and U is about 2 or 3 electron volts, gives you exchange constants of about 140 millivolts. So that's quite large. And when you work out what the effect of that on the spin waves is, you find that the highest energy spin waves are actually energy of 2J, and these can be up to energies of 300 millivolts there, which is one of the highest for super exchange antiferromagnets. You can have super exchange antiferromagnets. Another cuprate, deuterated copper formate, where the coppers are a long way apart, has exchange constants which are 100 times less than this. So you can get a wide range of them. But to get a high one, you want to have this, very long, very good overlap between the neighboring atoms. Keep them close and have an oxygen orbital. Okay, so that was super exchange. The next thing I'd like to say something about is the Linhart function and the exchange interactions in metals. Okay, so an important thing in metals is the wave vector dependent susceptibility, which, as we saw in the last lecture, the way you think of this is if you could do a thought experiment where you put on a spatially varying field. So we can call it B, so it would be BQ, and then it would be like sine QX or something, spatially varying field. This is a microscopically spatially varying field, with the wavelength comparable with the separation of the atoms, which is very hard to do in practice, of course, but one can do it with a neutron when you do a scattering experiment, and then that's going to induce a spatially varying magnetization. And we take the ratio of these two things, and that is our wave vector dependent susceptibility. So it tells us the response to a spatially varying field. So one can also do the calculation corresponding to this in perturbation theory to perturb the system with a spatially varying field and find out what the what the spatially varying magnetization is. And if you do that for metal, you come up with this expression here, which is called the Linhart function. And what you find is that the effect of this perturbation is to redistribute the occupation of the states near the Fermi energy. You have to take a picture where you actually include two Fermi surfaces with spin up and spin down, okay, and then you will find that you will switch some states from some electrons from being spin up of one wave vector to spin down of another wave vector, and that's how you construct this spatially varying magnetization. Okay, so so if you look what this this means, then this is the Fermi function at the top, and you consider the Fermi function, Fermi Dirac function for two states. Okay, so if the energy of your state is comes out to be above the Fermi energy, then this would be 0. So this might be 0. And if the energy of the state's below, this would be 1. Okay, so we've got 0 minus minus, or 0 minus 1 as a sign issue here, but let's not worry about that. Oh, well, maybe it's taken care of by these two states here. So the energy of our final state is going to be higher than the initial state. Yes, so there's another minus sign here. So if you consider these two states, because this one is occupied and this is unoccupied, that gives you a contribution on the top here, and then the energies here are the right way around. This will give you a contribution to the susceptibility. Okay, so to work out the Linhart function, then you've just got to go over all of your. You can write a little program to do it with a one electron a band like this. You go over all the k states and evaluate the sum, and that will give you the susceptibility. And the states that contribute to your sum will be ones where the initial state is below the Fermi energy and the final state is above, as I've drawn here. Okay, so that's the Linhart function. In fact, if you set the difference in states to be 0, so the difference between the states is Q is 0 here, then you will get the normal susceptibility up here. So the way I've labeled this just is the original. The K's represent the electron states. The Q is the obviously the wave vector of that we're probing. So it would be the if you're doing experiments, say neutron scattering, Q would be the difference in the momentum of the incoming and outgoing neutron if you wanted to measure it. Okay, so the Linhart function you can work out analytically with for 3 simple cases. If you take a Fermi surface in 1 dimension, 2 dimension, or 3 dimensions, you get these 3 functions here. So this is the Linhart function as a function of Q for a 1-dimensional Fermi surface, i.e. just 2 electrons moving along one direction, along kx, for example, and then they would have 2 points for the Fermi surface, as it were. So this would be K. Here's our 2 points, and then so this would be like 2kF. And you can see in 1 dimension, there's this one here. It has a sort of a singularity corresponding to excitations across that. And then in 2 dimensions, it's a circle. This circle, and then you've got also a sort of a step, or a cusp, I suppose, with the Fermi wave vector, and in 3 dimensions it doesn't really. There's a point of inflection at 3 dimensions. Yeah. So that's the that's the Linhart function as a function of Q, and here we've just normalized it to 0. So actually this would be the normal susceptibility, actually, the Pauli susceptibility at this point. It's normalized to the Pauli susceptibility, I suppose, this function. So these are the three simple cases. So people often talk about nesting and giving these this structure. So what do they mean by that? So probably that's a picture that is most obvious in one dimension. So if one had actually had a three-dimensional system, I think I've got some pictures of those in a minute, but we have a three-dimensional system, but if it has bits of sheet of Fermi surface, so this was a bit of sheet of Fermi surface here and here, so this would be like Kx and Ky, then this sort of would look like it had a one-dimensional component inside a three-dimensional system. And so this would give you a peak in the susceptibility corresponding to this this wave vector here. Okay. One can actually, once one's computed the wave vector dependent susceptibility, you can invert that and think of what the response would be to a point in the system, in the sense that if we have an atom and it has a moment, then how would the region around it respond? So one can get that by Fourier transforming the Linhart function that we've obtained. And what one finds that if one has this case or this case, and then Fourier transforms that in the appropriate way, the response in real space will have oscillations in it. I guess this is kind of related to ringing, because there's a cutoff. You know, in here we're responding less after some wave vector, or here we're actually responding a lot for this particular wave vector. Then one sees this this special wave vector come through in the response to the system. Okay, so this is the response. These oscillations are the response to a magnetic moment on a particular site, creating a local field, I guess, and then this is the response to it. And you can see these oscillations here. This is plotted as a function of 2 times the Fermi wave vector times r. It's oscillating away. Okay, so what does that mean? It means that if one has this system here, then one has a sort of probing another atom in another point in space, there'll be a coupling between the 2 atoms. This will this will mean that if we had an atom here and it creates these oscillations, and we put a test atom somewhere else, then according to which way around this this was, that the atom here would be preferred to have its spin pointing up or down. So this gives you a longer, this oscillating response, which is fundamentally something like this, the RK-KY interaction that one can have. So here's, it comes up in various contexts. RK-KY is when you put one impurity inside a metal, but another case is if you engineer a system where we have 2 magnetic layers, for example, and they're coupled through something that's not magnetic, but nevertheless has a Fermi surface, and it has a response function, the wave vector dependent susceptibility, then these 2 will be coupled according to the oscillations in this quantity when we work out what's happening in real space. So depending on the thickness of the layer, for example, here, these two layers, which might be ferromagnetic, could have a ferromagnetic or an antiferromagnetic coupling. So Albert Fert, for example, has worked on this and shown that according to the layer thickness, then you can get these different couplings, and you can see the effects of this in magnetoresistance, because electrons tunneling through this thing would have more difficulty tunneling through if they have to change their spin and so on, in this case compared to this case, and so they get these oscillations, which fundamentally is coming from these functions. Of course, the Fermi surface you'd have to work out what this was for the Fermi surface of copper. Okay, so in copper there are some necks in the Fermi surface, and those are the bits that give these the contributions to the wave vector dependent susceptibility. I think I even have a picture of that. Here we are. Yeah, so this is copper, and here's a copper Fermi surface. So if you multiply this up and then take a cut, this is the Fermi surface of copper, and these necks that come out here and here, they go and touch each other in the next Boolean zone. So if one makes a contour between the necks, you get this funny shape here. So here's the neck here, and you get this shape which used to be called the dog bone when people were measuring quantum oscillations, Das von Alpha in copper or something like that. They would measure this orbit. So this thing here, and then we've got bits of Fermi surface that are parallel across it here, and that gives you the contribution to the wave vector dependent susceptibility. Amazing. So in chromium, which is the sort of classic elemental incommensurate antiferromagnet, here's the Fermi surface of chromium. This is a bit of Fermi surface here, and then there's like a octahedron sitting in the middle of the Boolean zone here, and you get some nesting between these two bits of Fermi surface, which is also shown here. And the wave vector dependent susceptibility then in chromium if one was to plot it out, it would have sort of a peak at some wave vector. And when you put in the magnetic interactions in the chromium in some model, you find that it orders this peak. And here's a picture of the ordering of the magnetic moments in chromium. So it's actually a spin density waves. So in chromium, this peak actually means that the moment varies in space across different atoms. So these are all different atoms going along some direction in space. So so the point is, this can also come from this wave vector dependent susceptibility. Okay. I guess I don't really want to say too much about this, but well, the purpose of the last bit of the lecture was just to give an indication of the other sorts of terms that one might put in a magnetic Hamiltonian in general that come up in there's all sorts of systems, of course, in condensed matter. So we've got a term that represents an exchange interaction. And obviously in some systems such as the cuprates, then I've shown you that can be very, very important. But there are also lots of other terms here. So crystal field and spin orbit terms. And if you put a magnetic field, of course, there's Zeeman terms as well. So just to mention the crystal fields then, sort of connected to magnetism, crystal fields, but they're connected to the orbital magnetism. So if we put a magnetic ion in a lattice, then, as is shown here, then the orbitals of our atom then will there'll be the obviously there's a spin which we've been talking about, but we can also have orbital moments, okay, and the orbital moments then directly connected to the L quantum number. Okay, and when you have orbital these when you have your say your d orbitals in a transition metal sitting there in a structure, and then you've got other atoms around, then the orbitals, the d orbitals, so we've got sort of the d orbitals would then have L equals 2, and then you can have quantum numbers sort of m z would be minus 2 1 0 1 2. So there'd be a set of possible L values here, but these are all these states, of course, that come out are spherically symmetric states, and as you know, when you put it in an environment, then they pair up to give you these states like D2G and EG, and these are combinations of these states. Okay, so in this environment, then what happens is the orbital momentum becomes quenched, so the actual, when you add you can add minus 2 and 2 together, for example, and get 0. So you don't have a component that you'll see. But nevertheless, you can get two different energy states, such as the ones illustrated here. If one has a dxy orbital like this, then the charge density will point along these things, and then the dx squared minus y squared, it points along here. So the Coulomb interaction will be different, and you have this very different difference in energy of the states. Okay, so this is due to orbital effects then. But one can see this difference, for example. Recently, one probe that's be able to see it very, very directly is RIX, and here you can see the transitions between these two states. Here in lanthanum cuprate, for example, it's exactly this transition between these two states we're looking at, and that is a magnetic transition due to the crystal field. And here's an example in a 4F system where you can also see crystal fields. The interesting thing about crystal fields, say in a 4F system, is they can be much, much smaller. So this is a crystal field with electron volts, and here we have 10 millivolts. So when they're very small energies, they can then become very important in the magnetic properties of the system. Okay, just a few odds and ends then. We can have terms, anisotropy terms in systems, as well as the exchange, as well as the Heisenberg term. So the Heisenberg term doesn't pick out a particular direction, but once something orders, then the spins will want to point along a particular direction. So then an anisotropy term like this becomes important because it determines what direction a spin might point. Finally, another very interesting type of exchange interaction related to the Heisenberg interaction is a Derichinsky-Maria interaction here. So the Heisenberg interaction, we have an interaction of two spins that looks like this, as I described below, but But if you take symmetry, lower the symmetry of the system. So if you have a super exchange bond that looks, say, like this. So instead of the atoms being in a line, if they are like this, so they're no longer collinear, it means that you allowed other types of exchange interaction which don't have this form. Well, they have partly this form, but they also can have a more general form like this. Now, so if we cross the two the spins together, then we can multiply. The cross product is now a vector, which you can dot with a matrix, with a vector D here, and that gives you the that's a so-called Darcy-Moria interaction, and that's going to favor different types of order and so on. This D then has a particular direction which you can get from symmetry. So in this case, I think it has to be perpendicular to the plane. So the key thing is the reason this is happening is we've lost the center of symmetry of the system which we had here in the case where the atoms were collinear. Okay, so Darcy-Moria interaction can have nice consequences in giving you skyrmions, for example. These arise because of this type of interaction. Okay, well that was a quick tour of some types of exchange interaction, I haven't been able to cover everything, but just to give you an illustration of some of the things can happen in solids. So I'm going to have a pause. What time is it now? So maybe at 5 to 11, I'll talk a little bit about spin waves. Let's see. Is it recording? Okay, so this second bit is about spin waves. And here we see a lanthanum cuprate floating above the Harwell Science Campus, which is a place where you can measure spin waves. And here we have the ISIS neutron source. Under this green bit here, at the end of the arrow, is the synchrotron and proton synchrotron, and then there's a target station somewhere, I guess somewhere near the end of this blue bit. Oh, there's two target stations. So yeah, there's one at the end of the blue bit in here, and then one over here. One's for low energy neutrons, target station 2, and the second one here is for high energy neutrons. And here you have the diamond synchrotron, which also has a spectrometer that can measure spin waves, the RIC spectrometer. And over here, this is an old picture. We have the Didcot power station. These some of these cooling towers are now being destroyed, and a new power station built. So that's powering the whole thing. Okay, and the railway track goes to London, goes in front of this power station here. Okay, so let's have a look. So this is some data I had handy. So these are spin waves in lanthanum cuprate, which I mentioned before. You can see the spin waves go up to about 300 millivolts. And we can have the dispersion of the spin waves here. And this is a map of the intensity that you measure when you do neutron scattering. And you can see an interesting thing is that the intensity of the spin waves is much stronger here than here. This in spite of the dispersion curve going to 0 in both cases. So if we're in reciprocal space, that's this diagram down here. This would be the antiferromagnetic ordering wave vector, and this is the center of the Brouillon zone, or here gamma point. The spin waves are much stronger here than here. I guess one would expect that intuitively because this is near the antiferromagnetic point. But formally, what it's telling us is that the wave vector dependent susceptibility is much stronger here than it is here, in spite of the frequency of the excitation dropping to 0 in both cases. So that means that if you couple to it, to measure its magnetic properties, you see it. But these excitations here are still important, so they will still have energy in them and contribute to the specific heat and so on. I guess they're a bit like the dark matter that the astronomers talk about. They're there, and we can detect them indirectly through thermodynamic properties, but we can't see them through scattering. Okay, so this is the dark zone. So I said I'd tell you a little bit about spin wave theory. So you can make classical picture of spin waves, looking at the rotation of the spins classically, but you can also do a quantum mechanical, fully quantum picture of spin waves, which obviously is very useful if you're so looking at the polarization effects, the interaction of the spin, the neutron with the spins of the spins involved in the spin waves. So we'll just consider the s equals a half case again, and we'll call the two states spin up and spin down. Alpha and beta. Okay. So so this would be spin up, spin down, and you can describe the operators, quantum mechanical operators that have these eigenvalues. Then are the Pauli matrices. And here are the Pauli matrices for the spinor half. So we've got for the x is quantizing along x, we would have this one, the y, and the z. So obviously the z one is the one that's going to yield these two alpha and beta. These would be the eigenstates of this. Okay, so when I say spin up, I mean spin up along the z direction. Okay, so these are the operators then. And here's when we're using these operators, then we want to express the eigenstate as I've written down here, like this. So the matrix operator would operate on, say, a state like this. This would be eigenstate 1, 0. So the 1 is the amount of the up and 0 is the amount of down. So the basis vectors then for the 1, 0 are just the alpha and beta. Okay, so that's the setup then. So these normal operators, basis states, alpha, beta, and the eigenstates 1, 0 and 0, 0, 1. Okay, so then it's also useful to, when you're talking about spin waves, to define two new operators in terms of these guys. So we can define a new operator S plus as Sx times Isy, and then an S minus, which is Sx minus Isy. So these are called the raising and lowering operators, and that's because they raise and lower. So let's have a look at that. So if we multiply the, we can just get these results by multiplying these matrices together. So if we operate with the plus operator on the alpha state, which plus is already up, it can't go any further up, so we get a 0. If we operate on the if we operate with the plus operator on the down, we go from down to up, and so on. So with the minus, takes us from up to down, and if we operate on the state that's already down, we get a 0. Okay, I think this is just saying the same thing at the next line. That's the up, down, and of course the other operator, just if we were to operate on a spin up state with the Z operator, which we had, we'd get the eigenvalue half times the original spin, and if we operate on the down, we get the eigenvalue, which would be minus a half times the original state. Right. Okay, so when we rewrite the plus operator as this is the new Pauli, or the new matrix for the plus, and it's the minus. So it just switches the plus and minus when you're in the states that are not going to end up with a 0. Okay, so those are spin operators. So we're going to look, as I said, at the spin waves in a ferromagnetic chain, which is the simplest case, because the spin waves will be an eigenstate of the system. So we're just going to imagine that we have a bunch of spins in a chain. We're going to index them, obviously, going along the chain by this index here, and then there's going to be an exchange interaction J between the neighbors. So to get the Hamiltonian then would just be this thing here, where the angle brackets mean sum over the nearest neighbors. Okay, so you can do, sorry, delete that. The angle brackets mean a sum over pairs of atoms. So in each case, there'll be a pair of nearest neighbors. You can also write, so you see that often in theory papers with the angle brackets there, meaning the pairs, but you can also write the Hamiltonian as a sum over, a double sum, first over neighbors and then over sites. So what we mean by that is we have the site here, site J. So we choose site J in this sum, and then we choose delta being sort of plus 1 and minus 1 to sum over the nearest neighbors for each site. Okay, so if one does that, you don't want to count each pair twice, because you would get this given pair here from going to this site and going over that nearest neighbor, and then going to this site and going the other nearest neighbor. There you have this extra factor of a half if you use the same value of J here. So that's where the difference between the two things. Okay, so we'll find it easier to actually use this form for the spin waves with its extra factor of 2. The other thing which you often see in papers, or maybe they often miss it out because it's so they all know it, the theory people, right, is this: if we have the Heisenberg exchange interaction here, right, we can explicitly write this out as the components then. So I guess these shouldn't be vectors if we do that. I've written them as vectors. So this is S X and SY and SZ. Okay, but then one can rewrite this thing here in terms of the raising and lowering operators. So we saw that we just defined the raising and lower operators in terms of sum of Sx plus I Sy and so on. So if you just substitute those into this thing here, that actually these two and leave this one as it is, you can show that you can rewrite the Heisenberg interaction in this form here. Okay, so that's just the definition of operators. This is very useful for spin waves because spin waves are basically precession of spins in the XY plane, and the Z plane doesn't really do anything. This puts it into, this is very useful. You will see this, so this form is very useful. So this is kind of treated separately because it doesn't do much, and this is where the excitations occur. So if we just substitute this back into our Hamiltonian then, which basically means putting a factor of J and the sum, this is our new Hamiltonian for the chain. Well, obviously this sum actually is over everything here, not just the first term. Okay, so let's have a look at the eigenstates of that. Well, first of all, let's look at the ground state. So obviously the ground state of a fermionic chain, we're just going to have all the spins up. The ground state, we just make a product wave function of basically a product of basically an alpha here on this side, an alpha here on this side, and so where the alpha refers to the this spin, this spin, this spin, and that will be the ground state. So this is the product wave function. Then the pi is that means the product of all of the different states. So we're just going to sum over J from 1 to n number of chains. So we will write the product like this, or one can write it just as an abstract thing like this, where this just means that we write the value of all the spins from the first spin to the nth spin here, which is somewhat easier to see sometimes when we want to see the effect of propagating a spin flip through the chain, for example. Okay, so we can just test, first of all, whether this ground state is indeed a ground state by sticking it into the Hamiltonian. Okay, so we've got three terms in the Hamiltonian, three types of term. We've got this S plus, S minus, S minus, S plus, and the ZZ term. So the plus minus term operating on the ground state will give 0, and that's because let's have a look. So if we just take consider these spins here, J and J plus delta in the chain. Okay, we've got J and J plus delta. So if we operate here, this one will operate on this one. So this will be a lowering operator operating on an upspin. So remember, the lowering operator on the upspin makes it go down. And then the other operator here, the raising operator operating on this spin, which is an upspin, will give us a 0. You can't make the spin any more up. So if I just flick back, remember, if we operated with the upspin on the alpha, it gave us a 0. Okay, so because it's a product, it just takes 1 0 and out it goes. So this just goes along the chain and we'll give it all zeros. And in an analogous way, here the downspin, this one here, this upspin, will also give us a 0. So the terms containing the S plus, S minus, and S minus, S plus, when you operate on the ground state, will not contribute. They'll give you zeros. In contrast, the Z term, so we've got ZZ, will give us contribution. So here we operate with the jth one on this one here. So that will be operating on an alpha with an up, and that gives us a half times our alpha, and then again same thing here, and this time it will actually give another half. So each term in the series will give us a quarter. Okay, and then so then if we multiply by the number of terms in the series, that will be n. There's the quarter, and we've also got a j out the front in the Hamiltonian. So that will be our eigenvalue for the ground state. So just to go back, so we've got the z. So when we operate, did I write that down somewhere? So when we operate, oh yeah, here we are. If we operate with the z on the up, we get the half. That's basic eigenvalue equation. So where did we get to? We got to here. So we've got the eigenvalue. Okay, so we've shown that the ground state, if we substitute it in, is indeed an eigenvalue, and we get the energy of the ground state is this. I'll go back to red. I don't know, I seem to have lost the new here. Oh, this is the, okay, so this 2 has come from actually summing over for each pair, each site, we have to go to the left and then to the right. That gives us a factor of 2 here. That's the factor of 4 that came from the 2 eigenvalues multiplied together. And this factor of 2, which cancels with this factor of 2, is that's from the original Hamiltonian when we write it in this sum form. Okay, so we could also have done it as a sort of pair going up, and then these 2 factors of 2 wouldn't have occurred, and we'd get the same result. Right, so what's an excited state? So the simplest excited state from our ferromagnet, if this was the part of the chain, the simplest excited state would be just to flip 1 spin. Since we only, on each side, we only have eigenstates up and down. So if we flip 1 spin, okay, and then we're going to see what that does. So the way we're going to describe that is writing it like this. So we'll just put down spin L is flipped. Okay, assuming that we started with the ground state. So if we wanted to flip the ground state, we would use the spin, flip 1 spin in the ground state, spin L. We would use the lowering operator here on the lth atom, and we operate onto the ground state here. So this would be our 1 spin flipped, and then we could draw that out graphically here like that. Okay, so now let's operate on that state with the Hamiltonian, and so this is the term in the Hamiltonian involving the plus minus operators. Okay, and if we operate on our new state, our excited state, with this and sum over all of the things, then what's going to happen? Well, we saw when these terms operate just on regular pairs of up-ups, they give 0 because of the up operator operating on one of the ups. So as this basically, this is going to go through the whole chain, and it's going to go and pick out the interesting site where we've got a downspin. Okay, so if we look what happens then, so if we choose, if it goes through now, and this if J picks out the lth atom in the chain, and the J plus 1 is this one, then what's this going to do? Well, J plus the alpha atom is going to put that up spin and give us the give us an up there, and at the same time the J plus delta, the next one in the chain, is going to have a down spin, and then that's going to go down. So this effect of these two operators, it's going to go along and it's going to move the spin flip one up the chain, and then when we operate on the move this along one more, it'll do the opposite. It will move the spin flip one down in the chain. So we're going to get these two contributions here from operating with those operators. Sorry, this is going to move it one way and that's going to move it the other. So operating with this is going to give us, we're going to start with this state, down spin with on the L, and then when we operate with those, we're going to get a down with L minus 1, and then the one with a down with L plus 1. So so when we operate on the spin wave state, these things are not going to give 0. It's going to give this related state where we've propagated the spin flip along plus and minus. Okay, but obviously that's not an eigenstate because it's different to the original state. But we can use this to construct an eigenstate if we're clever. But before we do that, let's have a look at the effect of the the other operators. So that was the Z operators. So the ZZ operators operating on this thing with one spin flipped, they'll go along the spin. Remember, when it just operates on regular operators, then it gives you back the same operator with the factors. When it comes to this this spin down, it will give us will also give back the same thing, but with a different eigenvalue, with a minus spin eigenvalue, and there'll be two occurrences of that in the chain when it operates on these two, and then when it operates on these two. So basically, the eigenstate we had before had n. When we went along the chain, we had n, and now we have n minus 2 because of this spin. So the Z bit is going to give us back the original state that we tried, our trial state, with a factor. So that's fine. So this is going to so in contrast to the other ones, it's a kind of it's an eigenstate already of these guys. Okay, so how do we get around this thing that when we operate with this, we produce these two? Well, what you do is you actually you make a sum of these guys over the whole chain, and so when you operate, you produce a sum of these and a sum of these, and you can see that since you're over the whole chain, it's likely that you can construct a state that actually can be an eigenstate. So let's have a look at that. So in fact, the state that's chosen, if we try a new trial state where instead of just having one spin flip, we have a quantum state where we add up a set of states with one spin flip. So we start with a state with the first spins flipped, and then a state, well, dot, dot, dot to the end of the chain, and then add a state with the second spin flipped, and so on. So when we operate on these states, we would produce we would end up with we would end up producing from another of the terms, it would produce a state with a one spin flipped, and they would add up, and you can get another set with one spin flipped. But in fact, to make it more interesting, we're going to include a phase factor as well. We're going to construct a block wave basically in our states. So this is we're taking two steps here now. We're going to make a sum with the different one spin flipped at different points in the chain, and we're going to put a phase factor here in as well. And that is actually written here. So this is going to be our trial state. Okay, so it's going to be a sum of one spin flip states, each one with a block wave factor, and we're going to normalize, which is maybe less important here, but this turns out to be the correct normalization because we now have this sum. So basically the spin wave trial state then is a block function in spin. Okay, well, maybe I think at this point I'm not going to just go through all the different terms, but you can see it's worked out here. If we operate with the sums over our states with one spin flipped, you end up with this thing here, which is the original state block trial function plus this factor out the front. Okay, and then when we do the same thing to the with the ZZ term to our phase factors, then of course it's just going to bring out an eigenfunction out the front here, and this is the original block state. Okay, so this is the now we need to add these things together. And if we do that, basically what we're doing is operate with our block state here. Our block split, we operate with the full Hamiltonian. So the up up down down plus down, the up down plus down up operators, and the ZZ operator, and we collect them all together. We find this is what we get. Okay, this is the bit that came from the states with the effect of the up down and down up operators. We put the J's back in here. It's come from the Hamiltonian, and then this is the sort of this is what came from the ZZ, which is in fact the ground state energy minus the flipping of the two spins here. Okay, so this factor here is actually going to be a cos factor, and this is the dispersion of the spin waves. So what we've shown then in this is that a block function in spin is actually an eigenstate of the Heisenberg Hamiltonian, and the eigenvalue is this. Where we've recollected the terms a little bit. So this bit here was the original ground state. This two spins that have been, or this term that's come from the spin, one spin being flipped. If we throw that in with the excitations, that's this term here. So as you would expect physically, then the energy of the system is the energy of the ground state, which we had from just operating with the Heisenberg Hamiltonian on the ground state, plus the energy of the spin wave, which is we've got from operating the Heisenberg on the spin wave, and this and usually this is an exact eigenstate. Okay, so this is the energy of the spin wave. So you can see when k goes to 0, then we're going to get these two terms are going to cancel, and the dispersion and the energy of the spin wave will be zero. And then it's going to have a 1 minus cos dispersion, which is probably plotted out here. Yeah. So this is the dispersion curve then of the spin wave. Of course, this is going to give, if you expand the cos function, it's going to give a k squared dependence for small q, which is what happens down here. And then we've got the dispersion for our chain here. So we can extend this to 3 dimensions by just adding more exchange interactions along the other directions. And the effect of that is to basically add more causes, as it were, more of these phase factors, which you can see here. And so you would get, basically get a sum of causes for the dispersion in the other directions, and it would still be q squared here. So we've done the chain. We can also do the cubic system without having to do any more algebra, just from inspection. So there we are. Summary: spin waves are eigenstates of the ferromagnetic Heisenberg Hamiltonian. This is a very special property. It's not generally true. Antimagnetic spin waves, if we do this to an antiferromagnet, if we start with this state and flip a spin and do all those operations, what you would find is there's some leftover things that you can't get rid of. Even if you do the block state, it would not be an eigenstate. It would be approximately an eigenstate, because you can neglect some the first order terms, and that's what is called Holstein-Promakov spin wave theory, where you do that. You do the same procedure as I said, and you just you basically neglect the first these extra terms, and it turns out to work reasonably well. So although this procedure for antiferromagnets doesn't give you an eigenstate, the trial wave function is a good estimate of the energy of the antiferromagnetic spin wave as well. So this was the dispersion then of the spin waves in the ferromagnet, and we've come up with a physical picture of a spin wave, which quantum mechanically, a spin wave in a spinor half system is simply a single spin flip which can move through the system. And to create an eigenstate, you make a quantum superposition of having the spin flipped somewhere in your sample. Okay, so a spin wave is a delocalized excitation. It's a collective excitation which involves all of the atoms in your sample, okay, carrying a spin flip, which is quantum mechanically superposition of a spin flip on every site in the material. So if you sort of think of creating a spin wave in terms of scattering, right? So when we scatter elastically with neutrons, for example, we can get a Bragg peak, by scattering at all sites simultaneously, creating a wave which is derived from a scattering site, from a scattering at all sites together, and the wave interferes. So the spin wave is an analogous thing where we've created an excitation, a wave-like excitation, where we flip the spin at all the sites and made this quantum superposition. Okay, so just to rephrase that in a slightly different way, you could say, what is the spin of a spin wave? How much spin does it carry? And because it's a single spin flip, then spread out, it actually carries a spin of 1, okay, because we've flipped the spin. So that means that you can then do a little bit of conservation. So if you want to create this collective excitation, you have to have a particle that can change its spin by 1. So if you have a neutron, for example, the single neutron would come in with spin up. It would go to spin down, and this change in spin of the neutron would then be spread out all over all the sites in the material. And you could do the same with a photon. Now, a photon is actually more complicated. So the eigenstates of a photon, you know, would have spin 1, right? So you'd have a circular polarized photon would have spin 1, and then circular polarized the other way would have spin -1. But you can sort of choose superpositions actually of a photon to also allow it to change its spin by a half. So all is not lost. Photons can still excite the spin waves. Okay, so that was oh, it has an animation, but it's not going to work. I think that was about it. Yeah, this is this is a detail of Holstein-Primakov transformation, that you have to normalize your spin operators in a slightly different way to do that. But basically, it's what I just told you. So so with that, I'll stop and